Okay, my dear students, welcome to this new class. Last class, we defined the sum of two linear transformations and also defined the scalar multiplication of a linear transformation. And then we discussed some examples where how to find a sum of a two linear transformations and the scalar multiplication of a linear transformation. In this class, as I mentioned you in the last class, this space LUV, collection of all the linear transformation form a vector space. Under the binary operation addition, we define sum of a two addition in the last class as a S plus T of u is equal to S of u plus T of u, and alpha times S of u can be defined alpha times of a S of u. So these two under by these two binary operations, we try to show that this is a linear transformation, collection of all the linear transformation form a vector space, and that vector space called is a LUV spaces. Okay, so we start this. Let V and W be a vector spaces, and then LUV L of VW be the set of all linear transformation V into W is a vector spaces. Under the operation of addition and scalar multiplication, we have to define into a this form. That is already we have to define this addition and scalar multiplication into a this form, and then we show that this addition and scalar multiplication is a linear map. Okay, so that means we try to solve all the vector space conditions. So first is this is clearly this is closed under the addition, because if S and T are be a, if we take S and T are the element of L of VW, then we have to try to show that S plus T is also the element of L of VW. Then we can say that this is a closed under the addition, and also if alpha is the element of in the field, then we can say that alpha of S is also the element of a L of VW, means S and V. This is trivial, we have to already show that S plus T is a linear. So S and T are the two map from V to W. This means S and T both are the linear map, and then we have to already define S and T is equal to this form, and this is a linear map, this is a linear map. This means this is well defined as also. This means this is the sum of a two linear maps, and this is clearly this is also belongs to the we already show that this is equal to this S plus T is a linear map, and if it is a linear map, this should be belongs to the L of UV. This means S plus T is a closed under the vector. This is and the addition of these two linear maps. Similarly, this is also belongs to the L of VW. So this means by these two 1 and 2 condition, we can clearly say that this is closed under addition and closed under scalar multiplication. Okay, now we have to try to show that is a commutativity under addition is a commutative, associative, and also existence of identity elements. What is the identity transformation here? What is the inverse of a transformation here under addition? And also we have to try to form a vector space other condition or distributive form property and property. Okay, just start with the S1, S2, S3 are the these things, and alpha, beta are the scalars, and V be an arbitrary vectors into V. So we say that S plus V can be defined into this form by the definition, and then because this S1, this S, these are the element of S1, S2, and S3. All are the element V2. W is the vector spaces. So this is if we have a V is the element of a V, then S of S1 V is the element of a W. S of S2 V is also the element of a W, and so on. So this is the element of a, this belongs to the W, and this is also the element of a W, and W is a we have a vector space, and this vector space is a commutative. So this can be S2 of a V1 plus S1 of a V2. Some element are there. So because the vector space is by first we have to using the definition of sum of a two linear maps, then we have to using the, because this is the element of a W, this is the element of a W, and W is commutative because W is a vector space, and then the vector space means under addition should be a commutative, such as W1 plus W2 is the same as the W2 plus W1. So this means we can say that clearly S2 V is the same as S2 of V. This is the S2 V using the Vs1 into the commutativity condition of a vector space of a W. So this means this first condition for this is commutative. So this means by the again that using the definition we can say that S of V2 S of 2V plus S1 is equal to V. So by the definition of S1 plus S2, so this means we can say that S1 plus S2 is commutative under the addition, and now we have to try to show that this is associative. So again starting by S1 plus S2 V by the definition S1 plus by the definition of S1 plus S2 S3, again this is a linear, so this can be said S1 V plus S2 V, and then we can say that plus of S3 of V, and this is the element of a W, and this is the element of a W, and this is the element of a W, and W is associative under the addition. Though this can be written as a by the associativity of a W, we can say that V plus S3 S2 S3 V, and this can nothing but the S1 V, and then this can be written as a plus sign. We use that by the definition of a sum, we can say that S2 plus S3 V, and again using the sum we can say that S1 plus S2 plus S3 over V. So this implies that for this true for all V, so this can be written in the form of S1 plus S2 plus S3 is equal to S1 plus S2 plus S3. So this means this is clearly is associative. So that means we can say that this satisfies this condition. So this sum is linear transformation, collection of all linear maps is also is the associative. Now we have to show that there exists some linear transformation which is we have to just say that into this form. Now we take a zero transformation. If we take a 0 from V to V, 0 of V is always maps to 0. This is clearly this is a linear transformation. And then if we have any transformation, S1 is the element of a L of V comma W. So this means we can say that S1 plus 0 of V can be written as a S1 of V plus 0 of V, and now this can be written as S1 of V plus 0 of V, we have a 0. So this can be written as a we have a S1 of a V, and this is true for all the S1. So S1 plus 0 is equal to you have a S1. So this means case we can say that zero transformation from V to W is called is the identity of this transformation. This means this is 0 is clearly belong to the L of V comma W, and this transformation is called is a zero transformation is the identity element under addition for this LUV spaces is there. So this we can say that is clearly this. Now we have to find a element of a, if S is the element of a, this is now we have a S is a linear map, then minus S is also is a linear map, and then by because of minus S of V, we define as a form of a minus S times of a V. Then we have to just take a S of S plus minus S of a V is equal to, we have a S of V plus minus S of V, and this is equal to S of V plus minus S of V. This can be written as, again we have a S plus, this can be written in the form of this, and this is nothing but is equal to because of this. So you can, this is equal to 0 of V, and then we can say that S plus minus S is equal to 0 transformation. So this means every element S belongs to the LUV, minus S is also belongs to the LV W. So that means we can say that is a minus S is a linear transformation by the definition of this, and this by the definition of this again. So this is using the property of a W, because W is a subspace. So it is the element of a W, and this is also the element of a W, because if you have a U is the element of a W, then U plus minus U is always is a 0 vector. So by this we have to get the 0 transformation So this means we can say that clearly we have to show that this also satisfy the, we have to show that this is a, and under addition is satisfy all the properties of a vector space, means under addition is satisfy the closed, under addition is commutative, under addition is associative, and also under addition exists identity element. Identity element under addition is a zero transformation is the identity element, and minus, if S is the linear transformation, then minus S is also is a linear transformation, and the inverse of a S is a minus S. Okay, so now we have to just take some distributive properties. So by using this, we have to know that the product tool we have to define alpha times of a S of V can be written as a alpha times of S of a V. So this means we using this. This is can be written as alpha times of S of U, because of we use a alpha plus beta are the element of a field, or we can take a real number here, field of real number. So by the distributive product alpha times of S1 of a V plus beta times of a S1 of a V, and then again this can be written as a by the definition, this can be written as alpha times of a S1 of a V plus beta times of a S1 over V. This can be written as a alpha times S1 plus beta times S1 over V. For this is true for all V, so we can say that alpha plus beta S is equal to S1 is equal to alpha S1 plus beta S1. So this means we can say that this satisfies the distributive property also. So V5 is also satisfy vector space conditions. So this means this we can just write into the definition of alpha plus beta, and then we have to write into this form. Now other way we just take this form. So alpha of SV is equal to, this is like this, is equal to alpha times of this. So we can just write in the form of a alpha times you have a, because this is a using the sum definition. So S1 plus S2 of a V, and then again using the alpha times of a, you have a S1V plus alpha times of a, you have a S2V, then product rules alpha times of a S1 of a V plus alpha times of a S2 of a V, and this is nothing but is equal to S1 plus alpha times of S2 over V, and this is true for all V. So this we can say the alpha times of a S1 plus S2 can be written as a alpha times of S1 plus alpha times of S2 is also satisfy this condition. V6, so then we can say that clearly these two both the distributive properties as hold. So now we have a left is a alpha beta S1 is equal to beta alpha S1, this condition. So we just, and then two more conditions is to leads to verify, and then if these two conditions is hold, then we can show that this set is from a vector space under the operation of addition of a two linear map and scalar multiplication of a linear. Now we have to try to this S1 by the this is equal to this. Now alpha beta are the associated, this can be written as a beta alpha S1V, and this is can be written in the form of also this, we just say that alpha into beta times SV using the into W, and this can be written in the form of a, we have to write into this form alpha times beta S1V, and again we have to write in this alpha times of beta S1 over V by the definition of this product rules, and then this complete the field. We have to just say that alpha beta S1 is equal to, for this is true for all V. So we can say that alpha beta S1 is the same as the alpha times of a beta S1. So this is equal to this form. So it satisfies this condition. Now one more condition is left, and that condition is showing that 1 into V is equal to V, and that is this is equal to true. Alpha is equal to, we take a 1. So 1 into S1 is equal to 1 into S1, and this is nothing but is equal to S1 of a V, and then we have a 1 into S1 is equal to S1 for whole V belongs to this. So we just say that this is true, and then we have to verify all the axioms V S1 to VS 8 are satisfied, and that means we can say that this follows that this L of VW form a vector space under the binary operation addition of a two linear map and also the scalar multiplication of a linear map, as we have to define into this one. So this completes the proof of this theorem. That means this all LUV is a form a vector space under the sum of a two linear map and scalar multiplication of this. Okay, now we have to try to some questions related to this. Let V is equal to R2 and we have to take a L of V2 set of all linear maps from V2 itself, and then define a subset. We take a subset W is the form of a T of V is equal to 0 for all V such that x plus y is equal to this is I just say that this is sorry, this is x plus y means we have to just say that this is u plus v is equal to 0. We can write in the, this is no problem. We can take here is in place of this, we have fx is equal to 0 for all x belongs to this, x plus y is equal to. Now we have to prove that this W is a subspace of this LUV spaces. So for a subspace we have to show that there exists a linear transformation, at least one such a map which is belongs to the W. So we have to show that this conditions. We take a one is W should be, we have to show that is a non-empty for a subspace, and we take S and T are the element of a W, then S plus T is also the element of a W, and if we have alpha is the element of a fail, S is the element of a W, then we can say that alpha of S is the element of a W. If we succeed to prove these three conditions, then we can say that this W is a subspace of a vector space. Now we have to take a consider a 0 map, T0 I just say that suffix. So T0 is equal to 0 for all V belongs to V2, and then we have a clearly T0 is equal to for all V on the line x plus y is equal to 0. So we have to just say that on the line x plus y is equal to x plus y is equal to 0. So T is whole the line is 0. So T of 0 is equal to 0. This means T0 is on the line of this also. So T of 0 is the element of a W. So then W is clearly is a non-empty. Okay, so now if W is a non-empty, then we can say that this is clearly that T1, T2 are the element of a W and V is the element of a V2 with x plus y is equal to 0. So we take a T of V1 is equal to 0, T of V2 is equal to 0, and T of V1 plus V2 is equal to T of V1 is equal to 0. Then clearly T of V1 plus V2 are the element of a W. So we can just say that this V1 plus V2 is the element of a W, and then we can also say that W is V is the element of a V2, x plus y is the element is equal to, with the condition is this. Then we have a T of V is equal to 0 and alpha V is equal to alpha T of V is equal to, we have a 0 because T of V is the element of a W. So we have a this is equal to 0. Alpha T since W is a non-empty and close under addition and scalar multiplication, we conclude that W is a subspace of a V2. So this means we can complete this. Now we have to take a similar types question. Again we have to take a in place of a V is a vector space over a field F and U is a subspace of a vector space V. Define T from U to V to V. W is T from V to V, and T of U is equal to 0 for all restriction map we have to. Then we try to show that this is again is a this map is again is a subspace. This is a V comma V. So this is again true. We have to take a again T of 0 of U is equal to 0 map always. So 0 transformation. So at least T of 0 is the element of a W. So this clearly W is clearly is a non-empty. And now if W is a non-empty means we can show that take a two elements of a W. We have to take a S and T are the element of a W. Then as T of U is equal to 0 and S of U is equal to 0, then we take a S plus T of a U by the property of a S of U plus T of U, that is S of U is equal to 0, this is 0 is equal to 0. This implies that S plus T of U is equal to 0 means that by the definition we can say that S plus T is the element of a W. Okay, so now we have to just take these two condition is this for any u belongs to this is we have to take into 0. Now we take any scalar. So we have a this T is the element of a W. So this is for any u belongs to u, T of u is equal to 0. So we just take a alpha times of a T of u. This can be written by the definition alpha times of a T of u, alpha times T of u is equal to 0 is equal to 0. So we show that alpha times T of u is equal to 0. This implies that alpha T is the element of a W, means we take two different elements from the W and their sum of is again belongs to W, and scalar multiplication under close under scalar multiplication and close under the addition. So both the condition is satisfied. So if these two conditions are satisfied, then we can say that W is a subspace of a vector space of a L of V comma V. So the W is a non-empty and close under addition and scalar multiplication. So we conclude that W is a subspace of this. Okay, one more question we try. We have a V1 be a one dimensional vector space over a field of real and T V1 V2 be a non-zero linear transformation, and then we can show that the linear span of a V1 L of V1 V2 is equal to span of a T is equal to the span of a T. Now V1 is a one dimensional vector space is there. So V1 is a one dimensional vector space is there. So this means we have a basis of a V1 at least one element. So this is basis is equal to, suppose we have a V is the element of this basis. If V is the element of this basis, then we have to suppose U is the element of a V1, then U can be written as a linear combination of this basis alpha V. The T of U is nothing but is equal to, we can say that alpha times of a so this is a linear map from V to V. So we can just define to this form. So this means clearly one dimensional base, any vector U can be written in the form of a alpha times of a V. So this means T of U is the form of some like into this form. So let us start with this, because V is a one dimensional vector space over a field, T V be a non-zero linear transformation. Since dimension is equal to 1, let V be a basis for V1, because at least there is a one element in the basis, and for any x belongs to the V1, so x can be written as a in the form of a alpha V for some alpha is the element of a real number. Okay, so if alpha is the real number, then we calculate the T, S is the element of a V1 V2, then S is determined by the action of a V. S of V is equal to sum of beta times of a V, and for any x belongs to the alpha V belongs to the V1. So we have a we can just write as the form of this. We take this is S of x can be written as a S of alpha V, and alpha V means alpha by the property of a because S is a linear define L of S is the element of a L of V1 and V1. So this can be written in the for alpha times of S of V. S of V we have to assuming as a beta V. So this means S of x is nothing but equal to, we have a is the form of a alpha beta V. And now consider T is equal to, we have some gamma V. Since T is a linear and non-zero, this transformation is a non-zero transformation. This means gamma V should be not equal to 0, because this map is defined from T from V1 say to V2. So that means T of some V is the element of some scalar product into V, and this should be the non-zero transformation. This should be alpha should be, because V is non-zero, then alpha should also is not equal to 0. So this means is a non-linear transformation. This gamma should must be is not equal to 0. So gamma should be non-zero. So this means we can just write into this form. So T of x can be written in the form of a T of alpha of V from here, and alpha times T of V. Alpha times of T of V, we have a gamma of alpha times gamma of a V, and then we have a S of x is also, you have a alpha beta times of a V Tx. So this means this is nothing but is equal to we just write into this form. So S of x is equal to, you have a S of x is equal to, you have a we have this from so this is alpha from here we can just take. So this is alpha, and then this alpha this can be written in the form. So this means Sx alpha beta V. So this can be written as a here we have a from here we can just say that because gamma is not equal to 0, so this means 1 upon gamma, inverse of a gamma is exists, t of x is equal to, you have a alpha times of a v. So now alpha times of a v we have to this here, so we have to write s of x is the form of a alpha v, so we have to write a beta into 1 upon gamma of t of x. So this means is equal to beta upon gamma times t of x. So we just write into this form. Then Sx can be written as a linear combination of the vector of a Tx. So S can be written as a some linear scalar multiple times of a T. So this S is nothing but it is to belong to the span of a T. And now S was an arbitrary, and we conclude that L of S is an arbitrary vector we are choosing into a L of V1 V2. So if S is arbitrary vector in L of V1 V2, then we can say that L of V1 V2 is nothing but is equal to span of T. So just means we have to take an arbitrary element here, and we show that this is, it belongs to this. This is nothing but we have to try to show that this is S can be written as some scalar multiple times of a T, and if it's scalar multiple times of this means S is belongs to the span of a T, and then S is the span of a T, span of T. So this means S arbitrary. So we conclude that linear span of a V1 V2 is the same as a span of this thing, span of a T is here. Okay, so now I just stop today's lecture here. I just complete this lecture with the this problem. So today we have discussed the LUV spaces and try to show that L of VW or UV are the vector space under the addition sum of a two linear maps and scalar multiplication of a linear map we define as it is. Okay, thank you very much. In the next class we start the composition of a composition of a two linear maps, how to discuss it. So we discuss the composition of a linear map in our in next class. Thank you very much for this.